All right, let's dive into one of the biggest, most legendary feuds in all of computer science history. And believe it or not, it's a story all about a single command. I mean, just two little words that kicked off a debate that went on for decades about the right way to actually write code. A debate that honestly totally reshaped how we all build software today. So yeah, we're talking about the command goto and how it started a full-blown revolution. So the whole thing really kicked off back in 1968 with this bombshell of a statement from the legendary computer scientist Edsger Dijkstra. And he wasn't just, offering a friendly piece of advice. Nope. He was basically drawing a line in the sand. He claimed that the more a programmer used this goto command, the worse of a programmer they were. I mean, that's a pretty bold claim, right? It absolutely sent shockwaves through the entire programming world. And that, right there, leads us to the central mystery we're going to unravel today. What is this goto statement, really? And why on earth was it considered so harmful? I mean, what could possibly make a simple command so dangerous that one of the smartest people in the field wanted it wiped off the face of the earth? To figure that out, we've got to get into the fundamental problem Dijkstra was really trying to solve.
Okay, so let's get right into it and start unraveling this whole controversial claim.
Yeah, and I really want to stress this. He didn't just say, hey, maybe use this a little less. No, he wanted it gone, abolished, completely erased from all high-level programming languages. You see, to Dijkstra, goto wasn't just some clunky tool. It was a genuinely destructive one. He believed it fundamentally corrupted the way programmers even thought about their code. But to really get why he felt so strongly, we have to understand the core challenge that every programmer faces. And that right there brings us to the absolute heart of Dijkstra's argument. It all comes down to this gap, this disconnect between the code we sit down and write and the process that the computer is actually running in the background. Okay, so think about it like this. On one side, you have your static program. That's just the text, right? The code file sitting there on your screen. It's fixed, it's not moving, you can read it from top to bottom, but then you have the dynamic process. And that's what the computer is actually doing as it's executing that code, moment by moment. It's unfolding over time. Now, Dijkstra's big point was that our brains, our human brains, are really good at understanding static things, like words on a page. But we're not so great at visualizing these super complex processes that are constantly changing. So he said the goal of a really good programmer is to bridge that gap, to make the journey from the static text to the dynamic process as simple and as clear as you possibly can. And to make this idea really concrete, Dijkstra came up with this brilliant little analogy. So just imagine you're trying to count people as they walk into a room. You've got a variable. Let's call it n. Okay, step 1. The room's empty, so n is 0. Simple enough. Step 2. Someone walks in. Now, here's the key part. Step 3. There's this split second where you've seen them come in, but you haven't actually updated n yet. It's only at step 4, after you increment n, that your counter finally says 1 and correctly matches reality. You see the crucial point here? During that tiny moment at step 3, the value of n is, it's wrong. It's lying to you. The variable says 0, but there's a person standing right there in the room. So what your data means is completely dependent on knowing exactly where you are in that sequence of events. And that's why, to understand your own program, you absolutely need some kind of reliable map to track its progress. So, okay, if you need a map, how do you actually build one for your code? Well, Dijkstra proposed what is basically a GPS for your program, a coordinate system designed to track its journey with perfect precision. The first part of this GPS is what he called the textual index. And honestly, you can just think of it like one of those "you are here" markers on a mall map. It's a pointer that tells you exactly which line of code the computer is executing right this second. Super simple, and it works great for code that just runs straight from top to bottom. But what happens when you have things that repeat, like loops? Well, for that, you need a second coordinate, the dynamic index. And this is just what it sounds like. It's a simple counter. It keeps track of which loop you're on. Are you on the first pass, the second, the 100th? That's what the dynamic index tells you. And that's his brilliant solution right there. You put these two things together, the textual index telling you where you are, and the dynamic index telling you how many times you've been there, and suddenly you've got this perfect, reliable coordinate system. As a programmer, you can glance at those two values at any given moment and know exactly what your program is doing. The map is crystal clear, it's logical, it's easy to read. And now we get to the villain of the story.
So what does the goto statement do to this beautiful, orderly, logical map we just built? Well, to put it simply, it basically lights it on fire. This right here is Dijkstra's main accusation. See, the goto command lets a program jump from literally any point to any other point, completely arbitrarily. It's like teleportation with no rules. And the second you introduce that chaos, your nice, neat coordinate system just collapses. Your textual index starts bouncing all over the code, the logical flow is completely shattered, and your map becomes a tangled, unreadable mess. You lose the ability to reason about what your program is actually doing. And this contrast is just perfect. I mean, look at this. On the left, you've got a structured program. The flow is clean, it's predictable, it's like following a nice, clearly marked highway. But then you look at the right. That's a program loaded with goto statements. The flow is just chaos. It jumps all over the place, creating this tangled web that programmers gave the perfect name, spaghetti code. And trying to trace the logic through that, it's literally like trying to find the end of one specific noodle in a giant bowl of pasta. Good luck. And Dijkstra really hit the nail on the head when he said it. The goto statement is, in his words, too much an invitation to make a mess of one's program. It's just this primitive tool that lets a programmer completely ignore structure. And the end result is a program that's incredibly difficult for any human to understand later on. And yeah, that includes the person who wrote it in the first place. So, without a clear map, what are you even left with? Well, I guess you could, technically, track the program's progress by just counting every single action it takes from the very beginning. But Dijkstra had a name for that coordinate system. He called this simple clock utterly unhelpful. Because sure, it might tell you that the program has executed 10,000 steps, but that gives you zero insight into what it's actually trying to do logically. The meaningful map? It's just gone. Okay, so if goto is the path to chaos, what's the solution? Well, Dijkstra argued for a much more disciplined, more structured way of thinking. He championed what he called bridled alternatives, tools that actually restrain the program's flow in a good way to build a better, clearer path forward. So instead of the wild, lawless goto, he pushed for these structures. And these are going to look very familiar because they are the absolute building blocks of modern programming. We're talking about things like your conditional if-then-else statements, repetition clauses like while loops, and of course, procedure calls. Every single one of these controls the program's flow in a predictable, understandable, and totally manageable way. In other words, they keep our map readable. And this really brings us full circle, back to the main point. The goal is not just to get the computer to do something. The real goal is to write our programs in a way that lets us, the humans, reason about them effectively. The programming language itself should give us a clear and helpful coordinate system so that we, the programmers, have a fighting chance at managing the incredible complexity of the things we're trying to build. So in the end, this whole debate, which, remember, started over half a century ago about one single command, it leaves us with this really profound and timeless question. Are we writing code for the machines, or are we writing it for the other humans who have to come along later and understand it? The machine, after all, will run whatever spaghetti code we throw at it. The real challenge is, and always has been, writing code that other people can read, debug, and maintain. Dijkstra's argument was never just about goto. It was a powerful call to put human understanding first, in a world that's dominated by machine logic. And that's a lesson that is, without a doubt, more relevant today than it has ever been.